Morning to Ananda. Good morning. Please kindly confirm audio video on screen once. Good morning to Ananda. Please kindly confirm audio video on screen. Right. See, yesterday we have started the advantages of the bundle conductor system, right? Yesterday we have started the bundle conductor system advantages. And third advantage we said with respect to capacitors. Fourth advantage I am saying now. Fourth advantage with respect to bundle conductors. See, we have a term like surge impedance, or you can say characteristic impedance sometimes. Okay, so I will write the name surge impedance here. Surge impedance. Surge impedance. See, formula for this one is like root of L by C. Root of L by C. We will discuss in detail about this one while we move into the steady state analysis of light. Okay, so for time being, just take up the formula. Okay, root of L by C. And we have one more term like surge impedance loading. Surge impedance loading, or you can say ideal power transfer capacity of the system. So I'm writing here surge impedance loading. Impedance loading. So I will call in bracket it is SIL. Or we have one more name like ideal power transfer capacity. Ideal power transfer capacity. Transfer capacity. Okay. See, I am giving this formula SIL. It is a voltage square by surge impedance. Voltage square by surge impedance. Okay. Next thing. Listen, please. See, actually, by using bundle conductor system, we came to know that the inductance value was decreased and capacitance value was increased. Okay, so I'll say inductance value decreased, capacitance value increased. How in the sense? That's what we have seen in the second advantage and third advantages. Okay, yeah. So after saying that L decreasing, definitely ZC decreases. And after saying that C is increasing, denominator is increasing, then definitely ZC value decreases. So whatever the change you have, whether the numerator is decreasing or denominator is increasing, both will show to reduce the overall value. So surge impedance value decreases here. Surge impedance value decreasing. Now, if the ZC is decreasing, surge impedance loading will be increasing. Surge impedance loading will be increasing, we can say. Harsha, kindly check your audio system. Audio is okay? Audio is okay? Please tell me. Audio. Yeah, all are saying audio is okay. Okay, fine. Voice not coming, somebody saying. Harsha, kindly check your. Yeah, fine. Yeah, next thing. See, just we have to observe the difference between the second advantage and fourth one. What you have written in second advantage? Second advantage, what you have written? Maximum power transfer capacity. We have written a term like maximum power transfer capacity. Formula is Pmax equals to mod Vs into mod Vr by X. But now you have a term like ideal power transfer capacity. Ideal power transfer capacity, that is surge impedance loading, which is V square by Zc. V square by Zc. Okay. So these are some of the advantages, what we can say, some of the advantages. Now, let us do some problems in these bundle conductors, particularly in the view of GMD, GMR calculations, or you can feel inductance calculation. Okay. Yeah. So let's take first problem. Question number 1. Just go through it, what I am saying. Consider following single phase bundle conductor system. Bundle conductor system. Find the ratio between GMD and GMR. GMD and GMR of the system. GMR of the system. Find the ratio between GMD and GMR of the system. Okay. Yeah. So I'm showing the bundle conductor forward path. I'll say it is a forward path. And I'm showing return path in the question like this. Was the return path in the question? Next. So between these two, the gap is yes, you have. Between these two also we have a gap of S. And here also we have a gap of S. And here you see yes, distance. Yes. Okay. So next, rate diameter of each subconductor is diameter of each subconductor is diameter of each subconductor is 2 centimeters, and S equals to 10 centimeters, comma, capital D equals to 2 meters. I'm showing that capital D here. This is that capital D. Okay. So kindly look at this one. Kindly look at this. Consider the following single phase bundle conductor system. Find the ratio between GMR and GMD of the system. Okay. Find the ratio between GMR and GMD of the system. See, if he's asking this type of question, first of all, for single phase system, all of you listen to me. For single phase system, what is GMD? For single phase system, what is GMD? Distance between forward path and return path. That's it. GMD is nothing but distance between forward path and return path. How much is the distance you have between forward and return? Capital D. So capital D value itself is a GMD of the system. Capital D value itself is a GMD of the system. But if you are calculating GMR, I should take GMR of the forward path and then GMR of the return path. Geometric mean of these two GMRs will be the GMR of the system, and you have to find out ratio between the two numbers. What is asked? Following all of you, right? So let's move. Solution. I am saying in single phase system, GMD is nothing but spacing between the forward path and the return path. Distance between forward and return path, that is capital D. That is nothing but how much value? 2 meters he said in the problem. 2 meters he said. Whereas if it's a three-phase system, what you should say? It will be the value of cube root DAB, DBC, DCA. Like that we have to take for the three-phase system. As it is a single-phase system, simply capital D you can take. Okay, next. GMR is equals to GMR of the forward path. Let me call it A. Forward path A I am saying. And GMR of the return path I am saying it is B. So two terms I can say it will be square root. So you indicate here A is a forward, B is a return path. Okay, now let's take up the forward path here. Let's take up the forward path A. Simple. You have three conductors in this manner. Right? So just have a look here. These are the three conductors here. Let me give these names as A1, A2, A3. Let me give these names as A1, A2, A3. This is A1, A2, A3. Okay, next. What is the radius of each wire? Radius of each wire is how much? Diameter of each subconductor is 2 centimeters and the radius will come to be 1 centimeter obviously. Radius is equals to 1 centimeters. Radius equal to 1 centimeters. Somebody is complaining about vibration. Is there any vibration? No. So many saying good. Okay, no vibrations. Good. Yeah, my view means my video might have some sort of disturbance because of ceiling fan. Because of the ceiling fan, there is a change. There is a change. There is a vibration, little vibration. You look in this video of me. That effect is called as a stroboscopic effect. Stroboscopic effect. Okay, fine. Let's see. What is GMR of A1? See, while you are calculating, please listen to me. If you want, you write this statement also. Want to write this statement also? If you are calculating, GMR of a phase, you no need to consider the other phase conductors. GMR is a self distance of this phase itself. So we no need to consider the phase B conductors now. Okay, right. So what is GMR of A1? GMR of subconductor A1. Now, look here. Look here. See, first of all, what is self of A1? Self of A1 is R dash, 0.7788 into R. R dash. Next, mutual between A1 and A2. Yes. Next, mutual between A1 and A3. Yes. So three terms you have now. So we have to apply cube root of this one. So it will be cube root of R dash into S, you can say. That is GMR of A1. Okay. What is GMR of A2? GMR of A2. Self of A2, R dash. A2 to A1. Yes, we have. A2 to A3. Again, yes. Yesterday also we have discussed the same thing, right? While you are writing GMR of A1 and A2, first we have taken self of A1 and then distance from that A1 conductor to remaining conductors in the same phase. Distance from A1 conductor to remaining conductors in the same phase. Okay. What is GMR A3? GMR of A3, it will be self of A3, R dash, A3 to A1. Yes. A3 to A2. Also, yes, we have. So it will be under cube. So it is cube root of R dash into S we have. Yeah. Kindly follow the procedure. Only with respect to the examination. After getting GMRs of each and every subconductor, A1, A2, A3, then what is GMR of that phase? GMR of that phase is nothing but geometric mean of these three numbers. Okay. So GMR of the phase A bundle conductor, GMR of the phase A bundle conductor equals to GMR A1, GMR A2, GMR A3. So three terms you have under cube root. And you observe now, all these three values are equal. So this value is nothing but GMR of any one of the subconductor. That value is nothing but GMR of any one of the subconductors. Okay. What is GMR of subconductor A1? It will be cube root of R dash 0.7788 into what is the radius? What's that radius we have? It is 1 centimeter, right? Yeah. 1 centimeter. S into S value, what it's given in the data? 10 centimeters. 10 into 10. You please tell me how much is this number in centimeters? So 4.27 centimeters is the GMR of the phase A. 4.27 centimeters is the GMR of the phase A. Next, similarly, we have to think about the phase B. Means the return path. Phase B or return path. No issue with that. Don't ask me again, sir, single phase system, how you are saying it is phase A, phase B. Don't bother about it. Phase A is a forward conductor, phase B is a return conductor. That's it. Okay? Yeah. So B, phase B. So we have three conductors now. Let me copy this diagram again. Whatever they have given in the problem. Three conductors we have. Okay. So like this, you can say. So these are B1, B2, B3 conductors. I'll say it is B1, it is B2, it is B3. And radius of each wire is 1 centimeters. Radius of each wire is 1 centimeters. Okay, please listen, please listen. I want to make a small conclusion. I want to make a small conclusion. In the previous case, phase A calculation, all the three GMR values are equal. Hence, GMR of the overall phase is nothing but GMR of any one of the subconductors. Means I can say, in a bundle conductor, not in system, in bundle conductor. In a bundle conductor, if all the subconductors are having same GMR value, if all the subconductors are having same GMR value, then GMR of that bundle conductor is equal to GMR of any one of the subconductors. Okay, I will write that statement. If all the subconductors has same GMR value, then GMR of bundle conductor will be the GMR of any one subconductor. GMR of any one subconductor. Any one of the subconductor. If all the subconductors has the same GMR value, then GMR of the bundle will be the GMR of any one of the subconductors. Okay, let's proceed with this now. Let's proceed. What is GMR B1? Anybody? What is GMR B1? Yeah. What is self of B1? Self of B1. R dash 0.7788 into R. B1 to B2. How much gap you have B1 to B2? Yes, is a gap. Yes. B1 to B3. How much gap you have? 2s. B1 to B3 it is 2s. So cube root of this is a GMR of B1. GMR of the subconductor B1. Next. What is GMR of subconductor B2? GMR of the subconductor B2. Just look here. R dash. Okay. What is B2 to B1? B2 to B1. Yes, sir. B2 to B1 gap is yes, sir. And then B2 to B3. Again, yes, we have 3 terms under cube root. So it is cube root of R dash into S into yes. That is GMR B2. GMR of B2. What is GMR B3? GMR B3. So I'll show you in the next slide. GMR B3. So can you move ahead? So please kindly confirm. So in the next slide, I'll show GMR B3. GMR of B3 first. Self of B3 R dash. And then you see B3 to B2. Yes, we have B3 to B1 2s. So I can say yes into 2s, and you have 3 terms. So you can say it is cube root. So cube root of R dash into S into 2s. Cube root of R dash into S into 2s. Okay. Next, observe now how is the GMR B1, B2, B3? How are the values of GMRs B1, B2, B3? Equal or unequal? Equal or unequal? Unequal, right? GMRs of B1, B2, B3 are unequal. Now, we have to take up geometric mean of these 3 numbers to tell about the GMR of the phase B. So I can say GMR of phase B is equal to cube root of GMR subconductor B1, GMR subconductor B2, GMR subconductor B3. Okay, so let's substitute these things now. So it is cube root of, okay, let's see, GMR B1. Cube root of R dash into S into 2S. Cube root of R dash into S into 2S. Next, cube root of R dash into S into S. The next term, cube root of R dash into S into 2S. Okay, done. Next, let's continue with this. See, this cube root is common. Cube root is common, and we have whole cube root, means it will come whole power 1/9. whole power 1 by 9. Just observe the thing what I am writing. R dash into S into 2S. Okay, next. R dash into S into S. Next. R dash into S into 2S. Yeah. Whole power 1 by 9. Whole power 1 by 9. Okay. All of you stop writing. All of you stop writing. Just listen to the words, what I am saying. Stop writing, please. Stop writing. This is another way of calculating the GMR. This is another way of calculating the GMR, which will give same answer definitely. Tell me now, what are the distances of B1 conductor? Forget about cube root and all. Just tell me, what are the distances of B1 conductor? Self R dash, self R dash, B1 to B2, yes. B1 to B3, how much? 2s. You see, R dash into S into 2s. So these are the distances of the B1 conductor. Distances of B1 conductor. Okay, next. What are the distances of the B2 conductor? B2 conductor R dash, B2 to B1. Yes, we have. B2 to B3. Yes. So R dash into S into S we have. These are the distances of the B2 conductor. B2. Next. For B3. For B3. R dash into S into 2S. R dash into S into 2S. And these are the distances of the B3 conductor. Just listen to the words. After writing distances of B1, B2, B3. Count how many numbers you have here. Count how many numbers you have. Total 9. Total 9. So I should take whole power 1 by 9. I should take it as whole power 1 by 9. So this is another way of calculating the GMR. It's another way of calculating the GMR. Okay. So let's write this calculations quickly. R dash 3 times we have whole cube. 0.7788 into 1 centimeter whole cube. Next. Yes, how many times you have? 6 times. So you can have 10 power 6. And you have 2 into 2, 4, whole power 1 by 9. Whole power 1 by 9. Yeah, please tell me how much is this number? GMR of phase B, 4.98 centimeters. 4.98 centimeters. Now, you have to take geometric mean of GMR of phase A, 4.27, and GMR of the phase B, that is 4.98. Okay, 4.27, 4.98 geometric mean will give GMR of the system. Cube root of 4.27 into 4.98 under root. How much is this? Tell me please. What is GMR of system? Geometric mean of these two. Yeah, all of you, please tell me. Square root. Oh, sorry, square root. Okay. So this value will be like 2 point, no, not 2.77. It will be 4.611. Okay. 4.611 centimeters. That is a GMR. 4.611 is a GMR. Okay. Now you have to find the ratio between the GMD and GMR. Na? So you have to take GMD by GMR value calculation. GMD by GMR value calculation. What is GMD? Already we have mentioned GMD. 2 meters. That is 2 meters. Numerator we have 2 meters. Denominator 4.611 centimeters. That also you have to keep in meters. Then only units will be cancelled out. 4.661 centi means 10 power minus 2 and you have meters. So it will be 200 by 4.611. So how much is this number? 200 by 4.611. So 43.37. 43.37 is that ratio. GMD to GMR ratio is 43.37. Okay, why is asking GMD by GMR value only means this is a value which will be deciding the value of inductance. This is a value which decides the value of the inductance per phase of that system what we are discussing, single phase system. Okay. So in this problem, what you have to think is, we have discussed about two types of bundle conductors with three subconductors, one in equilateral spacing, next one in flat spacing, and how to calculate GMR of that each bundle conductor that we have discussed in this what we call a problem. Let's take one more problem. One more problem I'll take to give further more clarity. See, Bhaskar, in case of single phase system, GMD is nothing but distance between the phases. Distance between the phases. Of course, you have to observe now that S value, what they have given 10 centimeters, is very, very less compared to the value of capital D. S value was very, very less compared to the capital D value. Okay. So let's take one more problem quickly. Just check. Consider the following three-phase bundle conductor system. Three-phase bundle conductor system which has GMD and GMR values. K1 into capital D and K2 into smaller, respectively. Okay. So in the figure shown, the spacing between subconductors in each phase, is capital R equals to 15 smaller, 15 smaller. Okay, full stop. The value K1 by K2 will be dash. K1 by K2 will be dash. Okay, so I am showing the bundle conductor now. It's a three-phase bundle conductor system. Yeah, one more thing we have to write. In bracket, R is the radius of each subconductor. Okay, so it's a phase A. This gap is capital R. This is also capital R. Small r is the radius of each subconductor. Phase A. Next, I will show phase B and phase C. Phase B here. Phase C. Okay. And this distance, phase A to phase B, is capital D. And this distance is 1.2 times capital D. 1.2 times of capital D. Yeah. Obviously, GMR in the sense GMR of the system. Most of the times, each and every phase will have same GMR value. If it is not the case, we should take geometric mean of the GMRs. Okay. So kindly look at this question, what I have given. Consider the following three-phase bundle conductor system. Okay. Which has GMD and GMR values K1 into capital D. Capital D I have shown some place here. Capital D is a distance between phase A and phase B. Between B and C, it is 1.2 times of capital D. Okay. And GMR value is K2 into small r. GMR value how much? K2 into smaller respectively. In the figure shown, the spacing between subconductors in each phase. He has shown here A1 to A2 Kepler, A2 to A3 Kepler, A3 to A4 Kepler, A4 to A1 also Kepler. And the Kepler value was 15 times of smaller. Kepler value was 15 times of smaller. What is smaller? Radius of the each subconductor. Okay. He is asking to find the ratio between K1 and K2. Means K1 by K2 will be how much? K1 by K2 will be how much? Okay. Yeah. See, whatever may be the style or way of asking the problem, whatever may be the way of asking the problem, ultimately he is asking us to find out GMD and GMR of the system. Ultimately, he is asking us to find the GMD and GMR of the system. The GMD value might come as a constant into capital D. How much is that constant that you have to find? GMR value will come as some constant into radius of the subconductor. And you have to find out the constant value. And we have to find ratio between the constants. Very simple question. Very, very simple question. All of you getting this one? All of you getting? Can I observe? Can I move ahead? Can I move ahead? Okay, fine. See, first of all, I will be finishing the GMD calculation. That's very easy, of course. So GMD, as already he said, three-phase system. Okay, one more thing. Did he mention anything about transposition? How can we take 1.2D? They have given that in the problem, Mona. They have given that in the problem. Why are questioning the question? Okay, we will consider. We'll take care of that 1.2D, how it's going to be taken into the calculations. Okay, kindly listen to me. Did he mention anything about transposition? No, we have to assume it. Okay, not only that, we have to assume that the conductors are carrying balanced currents also. Those are inherent assumptions in each and every problem. I have mentioned you already. If it's an untransposed system, they will mention it in the question. In the question, they will mention it. Okay, so let's move. GMD is the value like distance between phase A and phase B and phase C, phase C and phase A, three terms, and you have to take cube root of this. Cube root of A to B distance, B to C distance, and then you should consider C to A distance. What is A to B? What is A to B? Capital D. A to B is capital D. Okay. What is that B to C distance? B to C, 1.2 times of capital D. 1.2 times of capital D. What is C to A distance? C to A distance. That is capital D plus 1.2D. It will be 2.2 times of D. Sum of these two will be 2.2 times of D. Okay. Three terms, I can say it is cube root. So cube root of capital D into 1.2D multiplied with sum of these two distances, that will be 2.2D. And you see D cube under cube root, D will come out of it, and you have cube root of 1 into 1.2 into 2.2. Can anybody tell me this constant number? Cube root of that? 1.382 times of capital D. 1.382 times of capital D value. So as he said already, GMD is nothing but K1 into capital D. Already he said in the question, GMD value is what? K1 into capital D. So capital D will be cancelled out, and the value of K1 is this constant 1.382. K1 is that constant 1.382. Okay, simple. Next, let's concentrate on K2 calculation now. Let's concentrate on K2 calculation. Look once, please. Look once. GMR is nothing but geometric mean of GMR of phase A, phase B, phase C. That's right. GMR nothing but geometric mean of phase A, phase B, phase C GMRs under cube root. Already you know that the subconductor configuration in phase A, phase B, phase C are identical. Subconductors configurations in the phase A, phase B, phase C are identical. Yes or no? Then obviously it will be resulting into simply GMR of the phase A. because subconductor configuration in each and every phase are identical. So you'll get this one GMR of the phase A. Let us concentrate on the phase A. Let us concentrate on the phase A. This is a phase A. This is the phase A. So I'll call it is A1, A2, A3, A4. A1, A2, A3, A4. Radius of each subconductor smaller. He said in the problem. Radius of each subconductor is smaller. That he said in the problem. Now, what's the value of capital R? 15 times of smaller. Capital R value was 15 times of the smaller. 4th root it will come. Good. Okay. Let's take. What is GMR of A1? GMR of A1. Simple, very simple to write. Just listen to me. We should take self of A1, then distance from A1 to A2, A1 to A3, A1 to A4. That's it. Okay. So R dash, self of A1 is R dash, A1 to A2, capital R, A1 to A3, how much distance you have? A1 to A3, how much distance you have here? Tell me please. A1 to A3. This is capital R, na? So it is root of R square plus R square. So it will be root 2 times of capital R. So it is root 2 capital R. Root 2 times of capital R. And A1 to A4 is again capital R. A1 to A4 will be capital R. So total 4 terms you have. So you have to keep this under 4th. So it will be like 4th root of R dash into capital R into root 2R into capital R. So I think all of you getting this. Is it okay? Is it okay? What is a GMR of A2? GMR of A2? GMR A2. So just observe now. Just I will read the distances. A2, R dash, small r dash. A2 to A1, capital R. A2 to A3, capital R. A2 to A4, root 2R. You will get the same numbers, right? Same numbers. What is GMR A3? We'll get same numbers. GMR A4, same numbers. You write all 4 subconductors as same GMR value. Same GMR value. Therefore, GMR of the phase A, nothing but GMR of the subconductor A1 itself. So you'll get this like 4th root R dash 0.7788 into radius multiplied with capital R. Capital R is 15 times of smaller and root 2 into, again you have 15 times smaller and into 15 times of smaller. 15 times of smaller. Okay, this smaller is repeated 4 times. You can take anything, anything you can take. Either you can take A2 and A4, A3. So anything you can take. That's your wish. I am following A1. If you want, you follow A2. No issue. Okay. See, I will be writing this one. GMR of the overall phase A. So you can see R power 4 under 4th root. R will come out of the root. R is coming out of the root, and we have 4th root of that constant. You observe 0.7788 into 15 into root 2 into 15 into again 15. Yeah. You please tell me this number, constant number, how much? 7.808. 7.802 times of smaller. And this is nothing but GMR of the phase A or GMR of the system also. GMR of the system. So as we know, GMR of the system is K2 into smaller. So that K2 into smaller will be 7.802 times of smaller. Then this K2 constant will come 7.802. Now, is asking to know this K1 by K2 number. K1 by K2. What is the K1 value? 1.382. 382. What is K2 number? 7.802. 7.80. Tell me what is this ratio? 0.1771. 1771. 0.1771 is the ratio. Okay. K1 by K2. 0.177. Yeah. So next thing. So look at this question now. Look at this question. In a 4 subconductor bundle, 4 subconductor bundle, the spacing between subconductors is conductors is capital D, small d. Spacing between subconductors is small d. Okay, next. The GMR of each subconductor in bracket individually is ds. The GMR of bundle conductor will be So it's not a type of fill in the blank question. We'll get some equation as answer. Okay. You write calculate the GMR of the bundle. Calculate the GMR of the bundle conductor. Better. Okay. So just check this one. Check this question what I have asked. It is asked in IES prelims examination one time. IES prelims examination, they have asked this one time. Just observe this question. See, we have a 4 subconductor bundle. Okay. Spacing between subconductors is small d. GMR of each subconductor individually. GMR of each subconductor individually is ds. What is the ds? Anybody please tell me. What is the ds? In our notation, what is the ds we should consider? That is r dash, right? R dash. 0.7788 into small r. Okay, good. Now, he didn't mention about what is the configuration of the subconductors in the bundle. He said simply we have 4 subconductors in the bundle. What configuration it is that they have not mentioned. In this case, we have to go with our standard configuration all the time. We have to arrange the subconductors in a square. Even though he didn't say it. Okay, so I'll write in standard configuration. This is subconductor 1, subconductor 2, subconductor 3, subconductor 4. Okay, you take 1, 2, 3, 4 subconductors. And distance between the subconductors, how much is it? Small d. This is a way how we have to consider the problem. Kindly observe here. This is the meaning of the subconductor spacing. Subconductor spacing is small d. This is the way of observation. Okay, and you have to find GMR of this bundle. Very simple. Just now we have solved a problem. First we should take r dash. That r dash is nothing but ds. R dash is nothing but the value ds multiplied with, and you know all the 4 subconductors will have same GMR. So you have to consider any one. Let us say 1. Okay, 1 to 2, small d. 1 to 3, how much you get 1 to 3? Root 2 times of small d. Root 2 times of small d. Okay, 1 to 4 is a small d. So you'll get this like fourth root of this. So you'll get this like fourth root of ds into d cube multiplied with root 2. ds into d cube multiplied with root 2. So I think all of you getting this one. Is this clear? This is one way of asking the question. So it's asked in ESC objective examination. ESC prelims. So next, let's have some small conclusion on these bundle conducts what you have discussed. Small conclusion I am taking that. Else, before going for that conclusion, so I'll say one more thing. One more thing. Just listen. I'm taking one heading here. I'm taking one heading. Yeah. Just look. N conductors. N conductors symmetrically arranged in a circle. In a circle. Just take up this heading. N conductors symmetrically arranged in a circle. We have to calculate GMD among these N conductors. We have to calculate the GMD value among these N conductors. Yeah. See, so I'll show this. See, we have a circle here. We have a circle like this. Circle radius is capital R. Capital R is a circle radius. Radius. Okay. Listen, stop writing. Stop writing. Just listen. Don't ask me again questions here. Just look what I'm saying. N conductors symmetrically arranged in a circle. I'll write here GMD, the heading itself, GMD among N conductors symmetrically arranged in a circle. Now, I'll show those N conductors in the circle. Conductor 1, conductor 2, and so on. Let's say conductor 3 also, and so on up to N. N conductors symmetrically arranged in a circle. What do you mean by the symmetrical arrangement? Symmetrical arrangement means what? Anybody? Symmetrical arrangement in the sense 1 to 2 distance, 2 to 3 distance, 3 to 4 distance, 4 to 5 distance, and so on, N to 1 distance. These values will be equal. Those values will be equal. Okay? Means distance between any two successive conductors, nearby conductors, will be equal. Means if you stand at 1, 2 is at same distance to me. N is also at the same distance to me by looking at 1. And by looking at 2, 1 is at same distance, 3 is also at the same distance. Okay, that's the meaning. Okay, next thing. See, is it having a practical existence or not? Don't bother about it right now. Don't bother about it. Is it having any practical existence or not? We'll think about the practical existence later. As a mathematical question, you feel it. As a mathematical question, you answer this. If N conductors are symmetrically arranged in a circle like this, what is GMD among these conductors? What will be the GMD among these conductors? In that situation, we should find out GMD of 1, 2, 3, and so on up to N. And we have to take geometric mean of these N GMDs that will give GMD among the N conductors. Okay, I'll write here GMD among the n conductors will be equal to GMD of 1, GMD of conductor 2, and so on, GMD of the conductor n, and n numbers you get whole power 1 by n. Whole power 1 by n. Okay, could you please tell me? Could you please tell me? Listen, could you please tell me? What is GMD1? What is GMD1? Geometric mean, listen please, listen please. We are not calculating GMR. We are not here to calculate GMR. We are concentrating on the GMD. Okay. GMD1 is the geometric mean of distances from conductor 1 to remaining conductors. That's it. That's it. Don't mingle power system here. Don't mingle power system here. Feel this as a mathematical problem, what I am saying. Okay, just listen. Number 1 to remaining all conductors existing means GMD of conductor 1 will be equal to 1 to 2 distance, 1 to 3 distance, 1 to 4 distance, and so on, 1 to n distance. And how many numbers you get now? Please tell me. How many numbers you will get it? Tell me please. How many? N minus 1 you will get. That number will be n minus 1, n minus 1. So, whole power 1 by n minus 1 we should say. Whole power 1 by n minus 1. And see, for example, if you calculate GMD2, it will come same as GMD1, right? GMD2 will come same as GMD1. GMD3 comes same as GMD1. GMD4 comes same as GMD1. All the n conductors will have same GMDs. As we know, GMD of conductor 1, GMD of conductor 2, all are equal to GMD of the conductor n. Then GMD among the n conductors will be GMD1 itself. GMD among n conductors will be GMD1 itself. Okay, so therefore I'll copy this. So this itself is a GMD among n conductors. N conductors. Yeah. So I'm not doing any derivation now. I'm not doing any derivation here. Directly I'm going to tell you what is this distances product. What will be this distances product? D12, D13, D14, and so on up to D1n. Distances product. Distances product. Okay. So this value will come like this value will come like capital R power n minus 1 into n lengths you get. Okay, I'm not going with any derivation as I said. If you calculate the product of those distances, it will come to be capital R power n minus 1 into n, where n is a number of conductors in that circuit. Number of conductors in that circuit. Okay, substitute that in the GMD equation. GMD among n conductors will be equals to capital R power n minus 1 into n whole power 1 by n minus 1. So it will be capital R power n minus 1 whole power 1 by n minus 1. It will be capital R only. And it is n power 1 by n minus 1. N power 1 by n minus 1. It's not arc length. It's not the arc length. You have to find out the center to center distance. It's not the arc length. Okay. For example, if you want to find these distances, we look at this diagram. If you want to find the distances from one to the other conductors, 1 to 2, 1 to 3, 1 to 4, and so on, 1 to n. These numbers you have to calculate, not the arc lengths. Okay, done. So this will be the GMD among n conductors. Now let's think about practicality. Kepler is the radius of circle. Already I have mentioned, no? Kepler is circle radius. Okay. Listen, please. Listen, please. See, so is -1 in denominator. Where is the denominator we have here? Where is -1? Where is denominator, first of all? n-1, not -1. Where you have n-1. 1 by n-1. 1 by n. Okay, listen. See, is it practical or not? That's the question. No, we don't have this type of practicality. But one thing is practical, that these n conductors, which you are arranging in a circle symmetrically, that you can use as a bundle conductor. Getting this discussion, whatever I have done is okay. Mathematically, it's okay, but there is no practicality of this. But what is practical means, these n conductors arranged in a circle, symmetrically arranged in a circle, can be a bundle conductor phase. See, if I say simply a bundle conductor, what you are interested to calculate? Is it GMR or GMD? What you are interested to calculate? If it's a bundle conductor, what you are interested to calculate? Is it GMR or GMD? Yeah. So it will be GMR value, GMR value. So let's take the next heading. Just I will extend that previous discussion. GMR of a bundle conductor with n subconductors, symmetrically arranged in a circle. Symmetrically arranged in a circle. Okay, so I will copy the same figure. This one only I am copying. This one. But now radius of each subconductor is smaller. That's the thing we have to identify. Radius of each subconductor is smaller. Let me write them. Smaller. It's a radius of each subconductor. Kepler is a radius of circle, already we said. Radius of the circle. Kepler is the radius of circle and smaller is the radius of each subconductor. Next. Simple. It's a very simple one. Now, what is GMR here? GMR of this bundle conductor. It's a bundle conductor. Call this as bundle. Tell me, what is GMR of bundle? We should take GMR of 1, 2, 3, and so on up to n. Then geometric mean of these n will be GMR of the bundle conductor. Clear? And obviously GMR 1, 2, 3, 4, and so on up to n are equal. Then GMR of the bundle is nothing but GMR of the subconductor 1. All n subconductors has same GMR value. Therefore, GMR of the bundle is nothing but GMR of the subconductor 1. GMR of the bundle is equal to GMR of the subconductor 1. Okay? GMR of bundle equals to GMR of the subconductor. See, GMR of subconductor 1, it will come like, listen, it will come like, first you should take R dash. means 0.7788 into small r, you should take r dash. 1 to 2 distance, okay, 1 to 3 distance, 1 to 4 distance, and so on up to 1 to n distance. Tell me how many numbers you get now in this product? How many numbers you get in this product? It will be the number n now. It will be the number n because d1 to d13 and so on up to d1n will be n minus 1 numbers, and we have r dash as the other number, so it will be whole power 1 by n we should take. Whole power 1 by n we should take. Clear? Whole power 1 by n. So already in the previous topic, we have taken the d1 to d13 and so on up to d1n without doing derivation. I said it as capital R power n minus 1 into n. That we will substitute. Okay, capital R power n minus 1 into n we will substitute here, and we have r dash whole power 1 by n will give GMR of the bundle. Okay, so GMR bundle is equal to r dash into capital R power n minus 1 into n, this whole power 1 by n, that whole power 1 by n we can say. This is GMR of the bundle conductor in which n subconductors are symmetrically arranged in a circle. Symmetrically arranged in a circle. So I think all of you getting it? Yeah. So next, okay, for example, so this is one of the prospective question in the examination. We concentrate here. Prospective question in the GATE examination mostly. Okay, 6 conductors. 6 conductors symmetrically arranged in a circle. Symmetrically arranged in a circle forms a bundle conductor. Forms a bundle. Okay. Radius of circle. Okay, you no need to think about it. Just tell me what is GMR? What is GMR here? GMR of the bundle, what you write? GMR of the bundle. First you should take R dash. R dash means what? 0.7788 into small r. Capital R value is the radius of circle. And power n minus 1. What is that n here? 6 na? So it is capital R power 5. N is 6. N will be 6. Whole power 1 by n in the sense 1 by 6. Just if you know the radius of each subconductor and circle radius, substitute here, you will get the GMR of the bundle. Substitute that, you will get the GMR of the bundle. Clear? Have you seen this type of conductor anywhere? 6 conductors symmetrically arranged in a circle. Have you seen this type of conductor anywhere? 6 conductors symmetrically arranged in a circle. Yeah. Yesterday we have shown it, right? Yesterday I have shown this diagram, I think. You may see this better. Yeah. This is a bundle. This is a bundle conductor. Exact view may not come in the circle, but these are arranged in the circle. These are arranged in a circle. You see 1, 2, 3, 4, 5, 6, 7. I think there is a overlap. Just check this. Just check this. Around 6 conductors you can observe here. 1, 2, 3. Here it is very clear. Here it is very clear. It's very clear. 6 conductors. Okay, that is a 765 kV line. Okay, good. Just check that in the tower peak it is clearly visible. Vikrant is saying, kindly check it. 6 bundle conductors. Yeah. So it's a 765 kV line where I have it's not Anaconda. Dear Shiva, it's not Anaconda. Anaconda means all the conductors should be in touch. All the conductors should be in touch. That's the Anaconda, but it's not Anaconda, it is bundle. Okay. Yeah. So it is a 765 kV line. 765 kV. Yeah. In these bundle conductors, what you have to concentrate mainly with respect to examination is how to calculate GMR. That's very important for examination. And what are the advantages of the bundle conductors? That's it. That's more than sufficient with respect to bundle conductors. Okay, and read the notes, whatever we have discussed till now. Yeah. Next thing. One small question I want to ask you. One small question I want to ask you. Just listen to me. For example, it is a single conductor, or I'll say bundle conductor. Directly I am drawing bundle conductor. It is subconductor A1 and subconductor A2. Gap between these two is S. Gap between A1 and A2 is S. Kindly listen to my words. Stop writing, and listen to my words. Bundle conductor, I said A1, A2, two subconductors. S is the spacing. R is the radius of each one. My question is, this whole we will call as bundle. That's okay. This whole we will call as bundle. That's okay. What is A1 conductor type? Yeah. Tell me please. Nobody is responding. Just look at the thing what I am saying. Type of conductor. See, what are the different types of conductors we said? We said solid, homogeneous stranded like AAC, and then composite stranded ACSR, and then hollow, different type, bundle conductor also one type. Okay. My question is very simple. It's whole we will say bundle. Whole we will say bundle. What is conductor A1 type? Till now, we said that as a solid. Till now, that we said as solid. But practically speaking, each and every subconductor is again a stranded conductor. Is an ACSR conductor. Okay, so in the bundle, each subconductor is again an ACSR conductor. So like this you can see. Okay, so this is an ACSR. Means what you have to understood is in bundle conductor, two or more number of ACSR conductors kept in each and every phase. Okay, so each subconductor in the bundle, in bundle is an ACSR conductor. Okay, so this is the end of the discussion of the bundle conductors. Almost everything we have discussed in this bundle conductor discussion. Next, I have to move to capacitance calculation. Actually, inductance calculation was over by this point. Now we should move on to the capacitance calculation. Before moving to that capacitance calculation, let us discuss about GMR calculation of stranded conductors. Till now we said all the time GMR of solid conductor R dash, simply 0.7788 smaller. But if it is stranded, how to calculate GMR of that? That we'll discuss. Then we will move on to the capacitance calculations. Okay, yeah, let's move ahead. I'll take the next heading like GMR calculation of stranded conductor. GMR calculation of stranded conductors. Okay. Yeah, let me complete this one. I will give 5 or 10 minutes. Okay. Yeah, we didn't completed that problem. What page you want, Vikrant? Please tell me. Previous problem only. This one, Vikrant. Sir, in the figure, 6 conductor is an hexagonal. Yes, definitely hexagonal only. Navdeep, hexagonal. It's a hexagonal. Yes. Okay, Vikrant, you please ask me after some time. Fourth one you are saying me. Is this? Please tell me the slide number. Please tell me the slide number. I think this one only, Vikrant. Sir, in circular arrangement, will there be any capacitance between each conductor? Actually, all the conductors are operating at same voltage, no, Vishnu. So we don't have any capacitance between the subconductors. Subconductor to subconductor, we don't have any capacitance. You ask me, that's a special doubt you are asking, why negative voltage is used for HVDC. You have to ask me separately, not in regular class, Ashwin. Okay, yeah. See, directly I'm moving with problem. Directly I'm moving with problem. Number one, two strands touching together. Two strands touching together. Okay, so I'll show this strand one. Yeah, strand two, I will show it the same. Okay. Strand two, also I will show it same. So each strand is having a radius of smaller. So you call it is A1, A2. A1, A2. See, this calculation will be similar to the bundle. Don't confuse, kindly don't confuse. We have many 765 kV lines in India. Just to type in internet, 765 kV lines in India, we have many. Okay, yeah, listen. So I have two strands, A1, A2. Two strands, A1, A2. So first we have to find GMR of A1, then GMR of A2. Geometric mean of these two will give GMR of the conductor, stranded conductor. This calculation will be similar. Calculation will be similar to bundle conductor, but you don't have S. We don't have S. That S will come in terms of small r. S will come in terms of small r. Okay, let me write first. GMR of strand A1. GMR of the strand A1. First, we should take R dash, 0.7788 into radius. R dash. What is A1 to A2 gap? Can anybody tell me? What is it? A1 to A2 gap? 2R. A1 to A2 gap will be 2R. Okay, so it is 2R. So total two terms you have to say square. That's it. What is GMR of strand A2? Strand A2. R dash, self of A2, A2 to A1, 2R under. So it is root of R dash into 2R GMR A1, root of R dash into 2R GMR A2. So after getting these two, GMR of the stranded conductor is nothing but square root of GMR of the strand A1, GMR of the strand A2. And as both strands are having equal GMRs, then GMR of the stranded conductor is nothing but GMR of any one of the strand. So it is root of 0.7788 radius 2R. So you can take that small r common, r square under root means r will come out of the root, and we have square root of 0.7788 into 2. Kindly tell me this number. Yeah, else you calculate it. Calculate it and take that value. Please complete it quickly. I'll move to next slide to take up some more calculations of GMR of stranded conductors. It's 1.248 times smaller. 1.248 times smaller. Okay, so I'm taking in the next slide. Second question. Three strands touching together. three strands touching together. Three strands touching together. You please draw that configuration. Please draw that configuration. How it will be looking. Three strands touching together. How it will be looking. I'll show. This is strand 1. I'll say strand number 1. Showing strand number 2. And strand number 3 should be in touch with 2 again. Strand number 3 should be in touch with the remaining. So I'll say this top one is 1, strand 1, and this is 2, and this is 3. The radius of each wire is smaller. Radius of each wire is smaller. Like a triangle, equilateral triangle. Okay, now you talk A1, A2, A3. Better for easiness in understanding. A1, A2, A3. A1, A2, A3. Okay, first, what is GMR A1? GMR A1. First, self of A1, R dash. Self of A1, R dash. 1 to 2. 1 to 2, 2R. 1 to 2 will be 2R. 1 to 3 also 2R, na? A1 to A2 2R, A1 to A3 also 2R. So it will be 2R. And here it is again 2R. So total 3, and it will be under cube root. So it is cube root of R dash into 2R into 2R. That is GMR A1. What is GMR A2? Tell me. Yeah, any shape you can take, all the 3 should be in touch. That's the meaning. What is GMR A2? Will it come same? R dash, A2 to A1, 2R, A2 to A3, again you will get 2R. And GMR A3, R dash, A3 to A1, 2R, A3 to A2, 2R. You will get same values. GMR A1, A2, A3, all the 3 numbers will come same. Then GMR of the stranded conductor. GMR of the stranded conductor is nothing but GMR of any one of the strand. Any one of the strand. Similar statement what we have done for bundle conductors. Okay, so I'll write all 3 strands. 3 strands as equal GMRs. Therefore, GMR of the stranded conductor is nothing but GMR of strand A1. And strand A1 0.7788 smaller, 2R under cube. So you can take that R come out of the root, and we have cube root of this number 0.7788 into 2 into 2. Okay, you please get this number how much? Please kindly get this number how much? 1.46 times of smaller. Good. 1.46 times. 1.46 times of smaller. Yeah. Next, 4 strands. 4 strands. I will give the diagram. I will give the diagram in the next case. Next case. Not problem. I will be keeping 4 strands. I'll say simply 4 strands not touching together. Just follow the diagram what I'm giving. 4 strands simply. May not be touching together. So this is the strand 1, A1 you can say. Strand 2, it is A2. Strand number 3, A3. Strand number 4, A4. Okay, so it is A1, A2, A3, A4. Next, radius of each and every one will be smaller. Radius of each and every one will be small. Okay. First, let's take GMR of strand A1 here. Yeah, good, good. GMR of strand A1. A1. Self of A1. What you can say self of A1? R dash. Self of A1 is R dash. Okay. What is that A1 to A2 gap? A1 to A2 gap 2R. A1 to A2 gap is 2R. Next. A1 to A3 gap. A1 to A3 gap. How much? A1 to A3. How much? Anybody? Tell me please. What's that A1 to A3 gap? 2 root 2R. You'll get that as 2 root 2R. Just listen. If you have any doubt, just listen. It's the center of A1. Center of A1. Center of A2. Center of A2. Center of A3. A1 to A2. 2R. A2 to A3 also 2R only, na? A2 to A3 also 2R you'll get. A1 to A2 2R, A2 to A3 also 2R. Now we should think about this A1 to A3 gap. A1 to A3 gap. The square root of 2R square plus 2R square. 2R whole square plus 2R whole square. It will come to be 2 root 2R. Else you can say root 8R. Any name. Any name you can say. 2 root 2R or else you can say root 8R. Yeah, good, good. Many of you are giving answers already. So I'll keep 2 root 2 times of small r. Next thing, next thing. What is it? 1 to 4 gap? 1 to 4 gap will be 2R only. 2R. So you have 4 terms here under 4 terms. And if you think about GMR, A2 distances, A2, 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 R dash, A2 to A1, 2R, A2 to A3, 2R, A2 to A4, 2 root 2R. For A3, N will get same, A4 will get same. All 4 strands have equal GMRs. All 4 strands have equal GMRs. Equal GMRs. Therefore, GMR of the stranded conductor is nothing but GMR of strand A1. So it is 0.7788 smaller, 2R, 2 root 2R, 2R, whole power 1 by 4. Whole power 1 by 4. How much is that? 1.722 times of smaller. That's the GMR of that conductor. GMR of that conductor. Good. Okay. So have a break for 5 minutes. After 5 minutes, we will continue with this one. We have to extend this one a little bit more. Take a break for only 5 minutes. I'll come back within 5 minutes. Okay. I have resumed the audio video on screen. So kindly confirm audio video on screen once. So actually, we discussed 3 problems till now. Yeah, so I'm continuing. See, 3 problems we discussed till now, 2 strands, 3 strands, and then 4 strands, right? But we didn't talk about what material, by what material these strands are manufactured. But we have not mentioned anywhere. Maybe our assumption is that all the strands are made by same material. Maybe all are made by aluminum. That's the assumption what we have made. So if you want to write, it's a all aluminum conductor AAC, and the previous one also all aluminum conductor. See, in the examination, if we didn't mention about materials of the strands, materials by which these strands are made, we have to assume it as AAC only, or we have to assume simply all the strands are made by same material. Okay, so it might be also AAC. Okay, done. For example, in the next problem, that is in the 4th one, yeah, class is up to 9:30. Class is up to 9:30. That's we should remember these values. No, Amrit, don't try to remember. Try to know how to derive it. It is one of the best way of answering in the examination. Rather than remembering these answers, we have to know how to derive it. Yeah. So let's move to the next question. I will show some change in that 4th one. So I have 4 strands now. 4 strands touching together. Maybe, okay, I'll draw it again. These are strand 1, A1, you can say, and it is A2. So this is A3, strand A3, and strand A4. This is A1, A2, A3, A4, and in this A1, A2, A3, these are made by aluminum, whereas A4 is made by steel. A4, it is made by steel. This is steel. Remaining all are aluminum. Okay, it's a composite stranded, you can say. Composite stranded. Now I am asking one simple question. Simple question. How to calculate GMR of this conductor? How to calculate GMR of this conductor? Just listen to my words. See, if a number of aluminum strands running in parallel with steel strand, means if you are sending some current, that current is going to be concentrated mainly in the aluminum wires. Current is going to be concentrated mainly in the aluminum wires. The steel wire current can be negligibly small. Steel wire current can be negligibly small, so that the effect of steel wire can be neglected in the GMR calculation. GMR is indicating magnetic flux linkages, right? GMR is indicating the magnetic flux linkages, but steel wire is not carrying any current. So that I can say steel wire effect can be completely neglected in the GMR calculation. Okay, so I'll write in GMR calculation, effect of steel strand can be neglected. Steel strand can be neglected. Effect of the steel strand can be neglected. Okay, next. The effect is neglected in the sense, for example, if you take up A1 with radius smaller, okay, what are the distances of A1? Self distance of A1, R dash, 0.7788 smaller. Okay, what is 1 to 2 gap? 1 to 2 gap is 2R. 1 to 2 gap, 2R. What is 1 to 3 gap? Just now in the previous problem we have done 2 root 2r. 1 to 4 we no need to take. 1 to 4 we no need to take. We feel that the steel wire is not there. We don't have A4 conductor and we should not disturb A1, A2, A3 again. A1, A2, A3 as it is we should take. A4 we have to remove completely from our calculation. Okay. Now what is the distance of A to R dash? A2 to A1, 2R you have, A2 to A3, 2R. That's it. A2 to A4 we no need to take. And for A3, R dash, A3 to A2, 2R, A3 to A1, 2 root 2R, and A3 to A4 need not to be taken. Effectively, how many strands you have now? All of you answer this one. All of you answer this one. Effectively, how many strands you have now? Effectively, how many? 3. Okay. Now I am saying directly GMR of this one. GMR of this stranded conductor. First, A1, distances of A1, R dash, A1 to A2, 2R, A1 to A3, 2 root 2R. These are distances for A1. Next thing, for A2, R dash, A2 to A1, 2R, A2 to A3, again 2R. These are the distances for A2. Next for A3, R dash, A3 to A2, 2R, A3 to A1, 2 root 2R. These are the distances for A3. Total, how many numbers you have? Tell me please. Total, how many numbers you have? 9. So you should take whole power 1 by 9. As I have discussed already, you should count up these total distances and you should take whole power 1 by. That will be the GMR of the conductor. GMR of the conductor. Why we are neglecting the effect of the steel wire? Because it is not carrying a good amount of current. Good amount of. Well, I think all of you getting this one. Next, let's say a small example in this case. Small example here is an extension I can say for this. Here, for example, we have 4 strands here, 4 strands, and this is made by copper. Let's say that A4 is made by copper. Then how to calculate GMR of this one? A1, A2, A3 are made by aluminum. These are made by aluminum. A4 is made by copper. A4, it is made by copper. They will give in the exam. Obviously, they will give in the exam. If they didn't give, how we can know which is steel? They will give in the exam. Okay. Tell me now. Tell me please. A1, A2, A3, A4, aluminum given in the problem. A4 is copper. How to calculate GMR of this one? Can we neglect the effect of copper wire or aluminum wires now? Can we neglect the effect of the copper wires and aluminum wires? No, we can't neglect it. We have to consider both. We have to consider the effect of aluminum wires as well as we have to consider the copper wires. But you see, current distribution is not in a proper way. Aluminum, sorry, the copper wire is going to carry more current compared to aluminum wires. So copper wire participation, listen my words please. Copper wire participation in the magnetic flux linkages is more compared to aluminum wires. Compared to the aluminum wires. In this situation, GMR value not only depends upon the conductor size, it depends upon material by which it was manufactured. Material by which it is manufactured. All of you getting my point? Current distribution you have to know first. Based on that only we have to decide this what we call GMR value. As in this case, right? In this composite case, in this composite conductor case, composite conductor case, composite conductor case, the GMR value depends on depends on the conductivities of materials materials by which the strands are manufactured. The strands are manufactured or made. Strands are made, or you can say manufactured. See, you can ask me a question that, sir, why you have not called this statement in the previous problem? Previous problem, one is made by steel, and you say that current is very less, but it's not zero, right? It's neglected, you are saying. So in that situation, I will say this is a GMR of the conductor approximately. So GMR of the conductor approximately, not exact. It's approximate GMR. So I think all of you getting this? Yeah. Done. But one more thing. We discussed some number of conductors in this stranded, some number of conductors in the stranded, but no one is practical. That's the issue. No one of these things is practical. Which is practical? Which is practical conductor? We have 7 strands arranged in what we call in a circular fashion. That is practical. For example, listen. Yeah, yes, Ramakrishna. Yeah, listen. For example, if you have all aluminum conductor, AAC conductor. Just follow this one. This is a bit important one for ESC prelims. This is a bit important for ESC prelims, as well as if you are writing any state examination. If you are writing any state examinations, this is very important one to be observed. This discussion what I am making. I have, yeah. I'll show that AAC conductor like this. This is one strand, maybe central, you can say. Central strand. Remaining strands I will show quickly. Outer strands I'm showing. Maybe it's a layer 1, what we have mentioned. Layer 1. Just look at layer 1. You see, all are made by aluminum. Okay. How many strands you have total? 7. Total number of strands will be 7. Just listen. Stop writing all of it. Just listen. See, for this, I have to find GMR. Let's take strand 1. Okay. If you want to take strand 1, first you should take self of 1 R dash. 1 to 2, 1 to 3, 1 to 4, 1 to 5, 1 to 6, 1 to 7. Total, how many distances you get for 1? How many self distances you get for 1? All of you. 7. You will get 7 distances. 7. R dash is also there, right? R dash 1 to 2, 1 to 3, 1 to 4, 1 to 5, 1 to 6, 1 to 7. Total 7 distances. Okay, next. For second strand, how many distances? For second strand, how many distances? 7. Assuming uniform distribution of current here. Assuming uniform distribution of current, or you say neglecting the skin effect. Neglecting the skin effect is one of the major rule what we are following in inductance calculation. Yes or no? Right. Number 3. How many distances? 7. Number 4. 7. 5. 7. Right. We have 7 strands. Each one is having 7 distances. Total how many? Total how many self distances you get now? 49. 49 self distances. The product of those 49 self distances, whole power 1 by 49. Whole power 1 by 49 will give GMR of this. Okay. So GMR of this AAC conductor exact will be 49 self distances product, 49 self distances product, whole power 1 by 49 units, whole power 1 by 49. Okay. Next, radius of each wire is smaller. I take radius of each strand. Radius of each strand. Now, let us take a solid conductor of radius capital R. Listen now. Kindly listen. What is the overall radius of this conductor? Anybody? What is the overall radius of this conductor? Anybody? What is the overall radius of that conductor? 3 times of smaller. 3 times of smaller. Okay. Let's take 3 times of smaller radius solid conductor. Forget about AAC now. Forget about AAC. I know overall radius is 3 times of smaller. That much radius solid conductor I am taking. That much radius solid conductor I am taking. This is cap. Now, what is GMR of this one? What is GMR of this conductor? 0.7788 into capital. Means you get 0.7788 into 3R. 0.7788 into 3R. How much is that? It is 3R only. Kindly check. 3D, 3 times of diameter. Already we discussed long back in AAC conductors or ACSR. Okay, how much is this number? Tell me all of you. Yeah, please tell me what is this value? Constant 2.336. 2.336 times of smaller. That's the GMR of a solid conductor with 3 times of smaller radius. 3 times of smaller radius. Okay, it is approximate. I'll say approximate in the sense. Okay. Listen. You may confuse now. Listen. All of you, stop writing. Listen. See, you have taken 49 self distances for this stranded conductor. That product whole power 1 by 49. This number may come like 2.17 times of smaller. This 49 self distances product whole power 1 by 49. If you do, you may get this GMR value like 2.17 times of small r. But if you assume, listen to me. If you assume that this is a solid conductor rather than stranded, if you assume that this is a solid conductor with the same overall radius of 3 smaller, you are getting this GMR value 2.336. So this is a GMR approximate calculation for stranded conductor. GMR approximate calculation for stranded conductor. How these two numbers you are getting? Anybody please tell me? Vijay Rani, just check that. How many times I have to tell you? This is a Kepler radius. Okay. What is the Kepler value? This is smaller up to this point. And what is this one? 2R. So it is smaller plus 2R. So it will be 3R. Yeah, listen to me. Listen to the words what I am saying you. Listen to the words what I am saying. Both numbers are a bit close. So in the examination, if it is a AAC conductor with number of layers in this manner, if it is a AAC conductor with a number of layers in this manner, you take the overall radius, multiply that with 0.7788. That will be approximately the GMR of that stranded conductor only. Okay. I don't know whether you have understood the comment or not. But very less percentage difference you get. One more thing, Shiva Prasad, if you push this into natural algorithm, that change will come down again. Yes or no? So GMR exact and GMR approximate are very close in this case. GMR exact and GMR approximate will be very close, or I'll say will be very close, very close if number of layers increases. So another new statement actually, number of layers increases. For example, you have taken only one layer. No? If you add one more layer, you do GMR exact, and you take that as a solid conductor with capillary radius equals to 5R. Capillary equals to 5R, and you calculate GMR approximate, and this approximate value will go very close to the exact, even compared to this. Okay, and moreover, all the things whatever I said now is valid only for the what? AAC conductor, not for ACSR. Valid only for AAC conductors. Okay. So I've written that last statement already. Is this one? So by this point, it's for AAC. Right? AAC only, not for ACS. 2.17R is that standard or derived? Actually, Pratyusha, you have to take those 49 distances product and you have to do it. You will get it. So I have written directly. Can we say 2.336 is approximate GMR of AAC with one layer, Shiva? With one layer. Yeah. Okay, next. Let's continue with the capacitance calculation. Already preliminaries or whatever the required things we have done. We know how to calculate GMD. We know how to calculate GMR. And if it is capacitance calculation, for all the things whatever we have discussed, if it is capacitance calculation, that 0.7788 will be missing. 0.7788 will not come. That's it. Okay. Yeah. So let's see. Calculation of capacitance of transmission. Capacitance of transmission. In a similar way of inductance calculation, okay. Let me take up the conclusions of inductance calculation, then we will move to capacitance. Okay. I'll take the conclusions on inductance calculation. After that, I will move to capacitance. Conclusions on inductance calculation. Conclusions on L calculation. Inductance calculation. Yeah. So let's see the conclusions what I'm writing. ACSR you have to calculate by the previous procedure. Listen to me. First conclusion. Already we know formula of inductance. I am not repeating it. 2 into 10 power minus 7 ln of GMD by GMR. 2 into 10 power minus 7 ln of GMD by GMR. Any system it is. Bundle conductors, single conductor, single phase system, any system, that's a formula which we can use. calculation of GMR and GMT will be little bit changed. Okay. What is the formula for series inductive reactance per phase? Series inductive reactance per phase. Series inductive reactance per phase. Very simple formula. Excel. That is 2 pi F into L per phase. Inductance per phase, sorry, inductive reactance per phase will be equals to 2 pi F into L per phase. Okay. See, actually, this L, I am keeping in terms of Henry by kilometers. I'm substituting that in Henry by kilometer as a number. Okay, what's the units of Excel? Generally ohms. It will mean ohms. And as we are keeping L in per kilometer, we should say ohm per kilometer. Excel in terms of ohms, and that will be per kilometer, Henry per kilometer. That's a series inductive reactance. Next one. What is the reactive power? What is the reactive power absorbed by the transmission line per phase? Reactive power absorbed by line per phase. I'll say it is QL per phase. Reactive power absorbed by the line per phase. So means you can say QL per phase. Okay. Two formulae I'll tell you. Just listen to my words. Listen to my words, please. Two formulae. One, I square into XL. Next one is V square by XL. Two formulae. First one, I square into XL. Second one, V square by XL. Both are correct. But you should say I is a current flow in the inductor. V is the voltage across the inductor. See, as it is a series element, this inductor, as it is a series element, it is better to write this reactive power in terms of current. Because whatever the line current or load current you have, that will be flowing in the inductor, and that is absorbing the reactive power based on that current value. So you can call this like the I square XL per phase. I square into XL per phase. Okay. I square into XL per phase, that is QL per phase. And QL 3 phase will come to be 3 times of that. And moreover, what is this nature of current? Anybody tell me please, what's the nature of this current? RMS current. You have to substitute the RMS current. Okay. Now let's say QL3 phase here. QL3 phase. So it will be 3 times of RMS current square into XL per phase. 3 times of RMS current square into XL per phase. Now let's extend a little bit more about this one. Let's extend a little bit more about this. QL per phase. I'm taking up. QL per phase is equal to IRMS square means okay, let me write this like IRMS square into 2 pi F into L per phase, na? 2 pi F into L per phase. Yeah. Always it is RMS only. What's the doubt in that? Always, if you write simply current voltage, these are RMS values only, na? Okay. 2 pi F is constant. Let's remove it, and you can say QL proportional to RMS current square into inductance. QL proportional to RMS current square into inductance. So I can say this QL proportional to this RMS current in case of AC operation. In case of AC operation, sinusoidal. RMS current, you will write it as maximum current by root 2. Maximum current by root 2 whole square into inductance. Maximum current by root 2 whole square into inductance. So you can write this like QL proportional to half L IM square half L Im square. QL proportional to half L Im square. Okay. What is that half L Im square? What is that name? Name. Anybody? Anybody tell me what is that half L Im square? Yeah. That is a peak magnetic energy. Formula for the peak magnetic energy, maximum magnetic energy. Okay. Peak magnetic energy. Peak magnetic energy stored in the transmission line, or you can say stored in the inductor. Stored in the inductor. Okay. Peak magnetic energy stored. I will ask one very simple question to you. Very simple question. What do you mean by reactive power? What's the definition of reactive power? Yes. What is the definition of the reactive power? Yeah. Anybody, please tell me what is the reactive power definition? Not use. Okay. Power drawn to develop magnetic flux. Is it power drawn to develop magnetic flux or electric flux? Or both? To and fro movement of power. Okay. Power consumed for magnetization. Okay, listen now. Listen. See, you see some YouTube videos, even by some famous companies also, electrical companies. They used to give various definitions for the reactive power. Think in a basic terminology. Think in a very, very basic terminology. You will get to know what is a reactive power exactly. Okay? Listen to me. I'm explaining what is a reactive power and all. Kindly go through it. Kindly go through it. See, this is one AC voltage source. And I'm showing a RL element like this. RL element. And this is voltage V. Okay. And this is the current I. And that voltage V, I am saying like Vm sine omega t. V, I am saying like Vm sine omega t. Okay, next. This RL load, impedance, mod Z at an angle is a phi. Impedance of that load is mod Z at an angle phi. Then how is that current I you can experience now? How is that current I you can experience? That will be some magnitude Im, Vm by mod Z. Vm by mod Z means Im into sine of omega t minus phi. Lagging current. That instantaneous current, it is Im sine of omega t minus phi. Like this you can get. Okay, next thing. What is the instantaneous power drawn by the load? Instantaneous power drawn by the load. What's the formula for instantaneous power? Instantaneous power, nothing, no VI conjugate, nothing. It is simply instantaneous voltage multiplied with instantaneous current. Instantaneous voltage multiplied with instantaneous current. So it will be small v, small I. What do you get now? Pm Im sine omega t minus phi. Sine omega t into sine of omega t minus phi. Okay. Now I will be taking a plot for this instantaneous power with respect to time. It's a time axis, you can say, and it's a instantaneous power. Instantaneous power axis, and it's a time axis. Yeah. Listen to me. If you plot that instantaneous power versus time, instantaneous power versus time, you will be getting definitely a sinusoidal variation. Sinusoidal variation. I might be getting that variation, something like this. Just observe it once, please. Like this, you will get that variation you are going to get in this manner. Instantaneous power with respect to time. Just listen, just listen. Very simple, very simple. Till now, I didn't said anything directly to you. I didn't said anything directly. Just I have taken a voltage source, load, instantaneous voltage, instantaneous current, instantaneous power. Done. Now, see, if I take up this instantaneous power versus time, particularly from 0 to t1 time, 0 to t1 time, we have some curve like this. What is the area under this curve? Can anybody tell me? What is the area under this curve? Name. What's the name for this area under this curve? Energy. That's going to be called as simply energy. So energy, okay. I will give some number. I will give some number for this energy. Let's say 20 joules is the energy of that area, 20 joules. And again, starting from this time T1 to T2. T1 to T2. What is the area under this curve? Again, energy. This area is also going to be called as energy. Okay. This energy I am calling like 5 joules. That energy I am saying as 5 joules. 5 joules. Very, very simple question. Very, very simple question. What is happening from the time t equals to 0 to t1? What's happening from the time t equals to 0 to t1? 0 to t1, what's happening? All of you? 0 to t1, what's happening? See, in that span, listen to me. Bhavana, just listen and answer the thing, whatever I am asking you. That's it. See, in the 0 to t1 time, there is an energy flow from the what we call this source to load. Means load is drawing an energy of 20 joules. Load is taking an energy of 20 joules. Load is absorbing an energy of 20 joules. Okay. From T1 to T2, what's happening? T1 to T2, what's happening? Energy is negative. Energy is negative, and moreover, this number is 5 joules. Means from load to source, we have a 5 joules of energy flow back. 5 joules of energy flow back. Following all of you. See, the same thing is going to be repeated in each and every cycle further and further. Means continuously, a source is delivering some energy to the load. And it is taking. Some part it is using. Some part it is leaving back to source. Again, source is delivering energy to the load. Some part is leaving back to source. Means whatever this 5 joules portion you are talking, 5 joules portion, this 5 joules of energy unnecessarily, unwantedly circulating from the source to load, back from load to source. Source to load, back from the load to source. This energy, we call it as reactive energy. Because it is not doing any work for me. Unnecessarily, unwantedly, it is circulating between the source and the load. This energy, we are going to name it as reactive energy. And that we are going to term sometimes like reactive power. That energy might be converted to power domain, known to be reactive power. Okay, so reactive power, or reactive energy is a component which continuously circulates between source and load and back from load to source. Load to source. Back from that load to source. Yeah. Sir, can the reactive power be consumed? That's what we are saying. Nikhila, what you have understood now? Sir, can the reactive power be consumed? What is that consumption? No consumption at all, right? One time source is transferring that to load, and other time load is feeding it back to source. There is no energy loss. Okay, now I will ask one more simple question. In the first 0 to T1 time, 0 to T1, 20 joules is flowing from source to load. 20 joules is flowing from source to load. Okay. In that, 5 joules is getting back to source. What is the difference we have now between the two? What is the difference here? 15 joules now. 15 joules. And where that 15 joules has gone? Where that 15 joules has gone? That is taken by the load. That's a real energy. That's a real energy. 15 joules is a real energy which is transferred to the load and used by the load. See, why it is happening? A load is taking some excess energy first. Load is taking some excess energy than its demand, and it is supplying back. Why it is happening means that is because of this energy storage element existing in the model. Right? So what the inductor behavior we have? What is the behavior of the inductor? No, 15 joules is not apparent power. Just listen kindly. 15 joules is the energy, real energy. Listen to me. Inductor, what it is doing basically, it is storing energy in one half cycle. In the other half cycle, it will be releasing the energy back. Inductor storing the energy in one half cycle. Other half cycle, it is releasing the energy back. Whenever it is releasing the energy back, that is going back to source. That's the thing what we are saying. Okay, so if you want to define simply reactive power, it's a quantity of power which continuously circulates from source to load, back from load to source again. Okay, so if you want, already we have written it. So reactive power is a quantity of power flows from source to load, and back from load to source. Okay, yeah. Now, could you please tell me? I'm asking one very simple question. Forget about all the things what you have learned earlier before this topic. Something you might have learned about reactive power. Forget about those things. Just listen to my words. Inductor, is it absorbing reactive power or delivering reactive power? Forget about all the things before this topic, what we have discussed, and whatever the thing you have in your mind. Just answer to the question. Inductor, absorbing reactive power or delivering reactive power? Both. Why you are sticking on to absorbing? It's doing both, right? In one half cycle, it is taking, other half cycle, it is delivering. We should have a dare to say this statement all the time. Dare to say fact. Yes or no? Both. Both. For example, listen. For example, in place of inductor, if we keep capacitor. In place of this inductor, if we keep capacitor, what that capacitor will do? Tell me please. What that capacitor will do? In place of inductor, if we keep a capacitor storing the energy in one half cycle, delivering the energy back in the other half cycle. So what that capacitor is doing now? Is it absorbing reactive power or delivering reactive power? Absorbing reactive power or delivering reactive power? Both. It stores, charges, discharges, continues. means the system is consisting some reactive elements, or power system network consisting some reactive elements by means of transmission line, our generator windings, transformer, and many equipment. We have reactive elements such as inductor and capacitor. What these inductors and capacitors are doing in the system is continuously those are storing the energy and releasing the energy back. Storing energy, releasing the energy back. But it is in opposite way. It's in little opposite way. Opposite way means if inductor is absorbing, capacitor will deliver. If inductor is absorbing, capacitor will deliver. If inductor is delivering, capacitor will absorb. That opposite way we have to think now. All of you getting? So as a convention, practically speaking in the energy domain, both are continuously storing the energy and releasing the energy back. That's okay. But as a convention for the analysis further, I will be sticking on to a statement that inductor is absorbing the reactive power and capacitor is delivering the reactive power. I don't know whether you have understood that universal convention or not. As a convention, it's not a fact. Is it a fact or convention? Is it a fact? Inductor absorbing reactive power, capacitor delivering reactive power. Inductor absorbing reactive power, capacitor delivering reactive power. Is it a fact or convention? It's a convention taken by us. Convention taken by us for easiness in the power analysis. Okay. So I can say here better as a convention. Inductor absorbs reactive power, capacitor C delivers reactive power. Delivers reactive power. Okay, I will say last statement here. Tell me, is it correct or not? Correct or not? If I assume that inductor is delivering the reactive power, then I have to assume that capacitor is absorbing the reactive power. Is it correct statement or not? Yes. Fine. That's it. Fine. Sir, why reactive power requires to establish magnetic flux in the circuit, sir? Shiva, why you are again linking that magnetic flux to the reactive power? I have explained all the things. It's open to you. If you have an inductor, you say it's a magnetic flux establishment or energy storage, energy delivery, all the things are same. Okay? Don't discuss reactive power only with respect to Sweta, we have to follow any one of the convention, right? That's why we are following this one universally. Why we have taken this convention means in the power analysis. In the power analysis, I can't say one is absorbing and the same element is delivering, right? The power analysis, if one element I am saying is absorbing, I should stick on to absorption only. I should not say it is delivering after some time. Okay, so I should stick on to a single element property as a consistent. Yeah. Okay, I will be stopping the class at this point. Tomorrow I will be continuing with what we call this capacitance calculation. Tomorrow the class will start at 6:30 only. Tomorrow the class will start at 6:30 only. 6:30 to 9 I will take tomorrow. 9 or 9:15 I will take. Okay. So if you have any doubts, you can ask me. I will make all the hands go. You can raise your hands if you have any doubt. Aveshri.
Sir?
Aveshri. Yeah, tell me.
Sir, in 100-page slide.
100?
100-page.
Okay.
So that capital R is equal to 2R only, no, sir?
Why? I have written here also.
Have you written R? I get doubt
This is
on
smaller.
that, sir.
This is smaller. From the center of 1 to surface, you have to measure the radius.
Okay, sir.
From center of 1 to surface, you have to measure the radius, right?
Yes, sir.
Then center to this surface, smaller. From this surface to this surface, 2r.
Okay, sir.
Then total will be 3r, right?
Yes, sir.
Mhm.
So how we got 49, sir?
Where is it?
There is
49?
any shortcut?
Not shortcut. I have explained elaborately. Number 1 will have 7 distances, I said.
Yes, sir.
Number 2 will have 7 distances.
Yes, sir.
And up to 7. Each and every strand will have 7 self distances.
Yes, sir.
Product of those 7 times
49.
49.
Okay, sir. That's it,
Each
sir.
one will have 7 conductors. So total number of distances will be 7 into 7.
Okay,
Yeah.
sir.
Yeah. Any other
Thank
doubt you have, Kavya?
No, sir.
Yeah. Imtiaz.
Good morning, sir.
Tell me, Imtiaz.
Sir, in page number 89, sir.
Page number 89.
Hi, sir.
Okay. Tell me.
Sir, in this, the given is GMR of each subconductor is TS, no, sir.
Individually.
Individually. In the bundle conductor, for individual and the whole system, it will be same, no, sir.
Yeah, just listen. Without participating that solid conductor into bundle, GMR is DS. That's the meaning. That's the way of understanding the statement.
Hi, sir.
Without
Sir.
participating, listen, without participating that solid conductor into the bundle, the GMR is DS. After participating it into the bundle, GMR will be definitely different because other conductors will show the effect.
Okay, okay, I understand. Before and after.
Yeah.
Sir, one more, sir.
Yeah.
After that, you could turn the page. GMD of N.
Which one?
GMD
Which
of
page?
N conductors, sir. Next stage, please.
Okay. Tell me.
Sir, actually, GMD is finding only for the forward and return part, no, sir.
I said already, it is not practical thing.
Yeah,
Listen.
sir.
Don't question the question. What I said, heading itself, it's not practical one. Just as a mathematical question you feel and you try to find. That's it.
Okay.
This question they have asked in civil services prelims examination one time. As an objective question they have asked.
Okay, sir. I forgot, sir. That's all, sir.
That's it.
Thank you, sir.
Ramakrishna.
Yeah, hello, good morning, sir.
Good morning. Tell me, Ramakrishna.
Sir, what is surge impedance loading means, sir?
We will discuss about it, Ramakrishna.
Okay,
Just,
okay, sir.
Listen. Actually, as we are discussing the advantage of bundle conductors, as it is a coaching, I have to give all at one point.
Yes, sir. Yes, sir.
Okay, rather than discussing in the textbook by going into the bundle conductor, that location.
Yes, sir.
Just follow it. We will, whichever the terms you are having some difficulty or newly introduced, that will be definitely repeated at some point. Okay.
Okay. Sir.
Yeah.
Okay. Thank you. That's it, sir.
Yeah. Gautami.
Hello, sir.
Tell me, Gautami.
100 page, sir. Sir, here AAC conductor means we are dividing conductors in like different conductors.
What's your doubt exactly?
My doubt is exactly means AAC conductor.
AAC already we discussed in the previous classes, right?
Yes, sir. Yes, sir. I'm asking a difference of solid AAC and bundle conductors.
Okay.
I mean,
see, listen.
Yes, sir.
This is solid.
Yes, sir.
Rather than making a big solid conductor, I am making small size of solid conductors.
Yes, sir.
Bunching together will give stranded.
Yes, sir. With same material, just we are dividing.
Same material. Rather than making a big conductor, I am manufacturing small size of conductors. Not cutting this conductor actually. Not cutting this conductor.
Yes, sir.
We are manufacturing new conductors again.
Yes, sir.
Okay, that is AAC.
Yes, sir.
Okay. See, same type of conductor you repeat in the same phase as A1 and A2.
Yes, sir.
This you take A1. And same conductor you repeat this side and you say it is A2. These two combinedly phase A you say.
Yes, sir.
That's a bundle.
Yes, sir. With the, some distance.
Some spacing, yes.
Oh, yes, sir. Here we don't have any distance. But
It's a single
There is
conductor
space.
system, right? It's a single conductor we are discussing, not bundle.
okay, sir.
If it's a bundle, you should think about that S value. It's not bundle discussion.
Yes, sir. Here we are using only single phase system, sir.
Single
Solid.
phase. It's a single conductor. Single conductor.
We are using in this single conductor for 3 phase or any phase.
Yes.
For
Single phase you
passing-
can use or 3 phase also you can use.
Okay, sir. Sir,
Okay.
another one, sir.
It's a single phase system.
Yes, sir.
A, B, C.
Yes, sir.
It's a 3 phase single conductor system. Okay.
Yes, sir.
It's a single phase single conductor system.
Yes, sir.
A1, A2,
Yes, sir.
B1, B2, C1, C2.
Yes.
What is this system?
3 phase
Bundle
double.
conductor.
Yes.
Bundle conductor. Okay. Understood the thing difference?
Yes, sir.
The conductor might be a solid or stranded, doesn't matter now.
Yes, sir.
If you replace this with a solid, simply it's a single phase single conductor system only.
Yes, sir.
But each conductor is solid. But here you can see each conductor is stranded.
Yes, sir.
And here also 3 phase single conductor system, whether the each conductor is a stranded or solid, whatever. And
Yes, sir.
similarly this.
Yes, sir.
Okay.
Okay, sir. Another doubt is we are assuming previous classes one is forward conductor, 2 conductors are return conductors. No?
In the 3 phase.
Yes, sir. Is it practically possible, sir?
In the balanced system, it is practical only, na?
Yes, sir. Means forwarding means 3 phase we are going to 3 phase power we are flowing through 3 phases, sir. Why we are? Yes, sir.
Gautami,
Yes, sir.
in one situation, one conductor will act as forward, remaining 2 will act as return.
Yes, sir.
In the other time in the same analysis,
Yes, sir.
other conductor might act as forward, remaining 2 will act as return.
Yes, sir.
I'm not saying that all the time A is a forward, B and C are return. I'm not saying that statement.
Yes, sir.
If one acts as forward, remaining 2 will act as return, I'm saying.
Yes, sir.
Okay, which one you select as forward, that's your wish.
Yes, sir.
Time to time it will change.
Yes, sir. Then under which condition ground is the return path, sir?
Under which condition? Ground is a return path.
Yes, sir. Neutral.
Ground will
like-
act as a neutral path, not what we call return exactly. For example,
Yes,
if sum of these 3 currents, phase A, phase B, phase C currents is not equals to 0,
yes, sir.
that current will flow in the ground, that will be acting as a neutral path.
Okay, sir.
Okay.
Okay, sir.
In that
In-
situation, if A is a forward,
Yes, sir.
then B, C, ground, 3 will act as return.
Okay, sir.
Hmm.
In same phase conductor, it is acting as a both forward and return conductor, sir. Means for another phase, it is acting as a return path, sir.
Yes. with respect to
Yes,
other conductor. For example,
Yes,
if I am
for
staying at
example.
conductor A, it is a forward.
Yes, sir.
If I stay at conductor B, A might be the return.
Return. Okay.
Ah.
Yes, yes. Sir, I have another doubt means while finding the inductance values, means both total when we are finding total inductance and self and mutual inductance, I have some doubts.
Okay,
Means
what's the
it
doubt
can-
here?
Sir, while finding the inductance value, there is means it is both the internal and external values are total inductance value means 0.4 into 10 power minus 9. Like how
What's
to
the doubt
find
in
it?
that? What's the doubt in that?
Total inductance means we are considering 0.4 into 10 power minus
That's
7.
LA plus LB.
Is total
I don't-
circuit inductance
That is only for single phase system.
only for single phase. Okay, sir.
For single phase, you will sum up, right? For three phase, you don't sum.
Okay, sir.
Hmm.
Yes, yes, sir. That's only, sir.
That's
Thank
it.
you, sir.
Okay.
Okay, thank you, sir.
Bhaskar.
Hello, sir.
Tell me, Bhaskar.
How we calculate GMR for ACSR conductor, sir?
Yes, sir. You have to follow the same procedure, Bhaskar.
But
Number of self distances you should consider. It's laborious. Yes.
means non-uniform current distribution, sir.
You neglect the steel wire. You said.
That means same AAC conductor, na, sir.
How it will be AAC, Bhaskar?
If neglecting the steel conductor.
One of the conductor you are neglecting, but that conductor is aluminum in the AAC.
Yes, sir.
The difference is there, no?
Okay, okay.
Getting.
Oh, yes, sir. Yes.
Hmm.
Okay, sir.
Any other doubt you have, Bhaskar?
No, sir. No, sir.
Shiva. Tell me, Shiva.
100%.
Okay.
So here we are calculating the GMR of the AAC conductor first, and like we take the same radius of a solid conductor and it turns out to be 2.36.
Okay.
So we are assuming that the approximate GMR of AAC conductor is 2.36. Is that
Yes. Yes. Yes.
And so is it for one layer?
Only one layer.
And then 91.
90, na?
91.
Okay.
Sir, I don't understand how you got R power n minus 1.
That's a derivation, I said, no. I will send it. Derivation. I have written directly.
Okay, that's the derivation.
Derivation part. If you want, I will discuss in one special class that derivation.
Sir, and then I have one last question. Sir,
What
how
is it?
that flux linkage got divided into internal flux and external flux? Like how we have to consider the internal flux formation and the external flux formation?
See, simply we have a conductor carrying some current. Hello?
Yes, sir. Yes, sir.
Conductor carrying some current.
Yes, sir.
Whatever the flux linkage is happening inside the conductor, we are naming internal.
Yes, sir. What I'm asking is that the internal flux is due to like eddy current formation.
No. That is simply due to current flow inside the conductor. That's it. Not
Okay,
eddy currents. Eddy currents and all we are neglecting, no?
Yes, sir. And the external flux is
Outside the conductor.
that links to the other conductor.
Maybe.
Okay, sir.
Yeah.
That's it. Thank you.
Avinash.
Hello, sir.
Tell me, Avinash.
Sir, you have told about the one copper conductor and 3 aluminum conductors.
Yeah.
Sir, how to find GMR in that? Means
You
what
have
is the
to take some current I, capital I,
yes, sir.
and you divide that current between them by using their what we call resistivities.
Sir,
Current
will you please-
division. The current division formula you have to apply.
Sir, but how will you please explain it in short, sir? Sir, will you please explain it in short?
See,
Means how to
we have You have two conductors, let us say. One is aluminum, other one is copper. It is
Yes.
having a resistivity ρ1, it's having a resistivity ρ2.
Yes, sir.
Okay, having same length and same area of cross section.
Yes, sir.
So obviously resistance R1 will be proportional to ρ1, that's it. Resistance R2 will be proportional to ρ2. You
Yes,
are
sir.
giving a current of I as an injection. Input current is I.
Yes,
Then
sir.
what is the I1 value? I into what you can say? Opposite one. Because you
Current.
feel these two are in parallel.
Yes, sir.
So it's a current I injection. So opposite one is a ρ2 by ρ1 plus ρ2.
Yes, sir.
That's the I1 current. What's the I2 current? I into ρ1 by ρ1 plus ρ2. Okay? Are you here? Are you hearing me?
Yes, sir. Yes, sir.
After getting these two currents, you find out the flux linkages of what we call first conductor, self and mutual between these
Yes.
two. Okay.
Okay, sir.
From that you will get inductance of this now.
Yes, sir. From flux
There you get a term as GMR. That will be definitely depending upon these values, ρ1 and ρ2.
Yes, sir.
Yes. Okay, getting?
Yes, sir. Sir, how to find the GMR from the means flux values?
No. See, you have to find out inductance. From that only we have to get the GMR.
Okay, sir.
For example, if you take up this psi1, what's the self here? I1 into self-inductance of this. 0.2 ln of 1 by R dash plus, because of second one, I2 into 0.2 ln of 1 by 2R. Okay?
Yes, sir.
And you have to take that I common from this. Psi1 is equals to I into, and you get ρ1 plus ρ2 is also common. And you have ρ2 into 0.2 ln of 1 by R dash first term plus ρ1 into 0.2 ln of 1 by 2R. And this you have to simplify to get it. GMR. Okay?
Okay, sir. Yes, sir.
It's very laborious one. And definitely that inductance value depends upon ρ1 root, right?
Yes, sir.
That's the intention to tell you. Self-inductance value depends upon the material here.
Okay, okay, sir.
Okay, any other doubt you have, Avinash?
Thank you, sir.
Yeah.
No, sir. Thank you.
Kumar,
Sir,
tell me, Kumar.
sir, for hollow conductor GMD, like in circle arrangement of n cycles with the touch
GMD.
for hollow conductor.
Why you are talking about GMD if you are saying hollow conductor?
Like if we given a hollow conductor, we have to calculate self inductance. Like
Then you have to think about GMR.
what about GMD, sir? GMD also.
Why you
like
are
one-
GMD is between one conductor to other conductor, mutual.
Okay, okay. Okay, sir. GMR.
Okay,
GMR.
tell me, what's your doubt, Kumar?
Same, sir. GMR. How to calculate GMR?
Now, how to calculate GMR of a hollow conductor? That radius itself is a GMR approximately.
Radius
Ah,
of
radius.
circle or radius of conductor?
Circle.
Can we do the GMR for a circle n subconductors? We do, sir.
You can follow same formula.
But here touching of each conductor.
Okay, you can follow same formula then also.
And also ACSR conductor can be treated as hollow conductor.
By removing the steel.
Yes, because of it is center, it's removed, it becomes hollow. Right?
But if you have only one layer, if you have number of layers, then this formula can't be used again.
Yes.
There, the thickness of the circle will be more, na?
Yes.
You have to identify.
Okay. Sir.
Okay.
Okay. Thank you, sir.
Smile.
Sir, good morning, sir.
Good morning. Tell me, Smile.
Sir, I have a doubt, but you already explained for other person.
Okay.
I have clarified
Yes.
it.
Any more
Sir,
doubts you have, Ismail?
any update about offline classes, sir?
I don't have anything. If I know, I will tell you. Okay. Smile.
Okay, thank you, sir. No more doubts.
Okay. Kushal. Sorry.
Hello, sir.
Tell me, Kushal.
Sir, what is the advantage of the reactive power in the transmission line?
No, advantage. Advantage, how you can say? What's the advantage? Tell me of reactive power from the explanation what we have discussed.
Means the stored power can be used.
Where?
No, sir, means the extra load is connected there.
Then that load also will draw from power from source only.
Okay.
Understood?
Sir.
There is no advantage
So
or
this
disadvantage of
power
reactive
flow
power.
will, this
Some-
reactive power will always flow in the transmission line, sir.
See, once if you place a line or a winding, definitely L and C will exist.
Yes, sir.
Yes or no?
Yes.
If L and C are existing, you can't avoid the storage and discharge of energy.
Yes.
You can't avoid it. Reactive power, you can't avoid it. Some people will say, I will make the net reactive power 0.
Sir.
Kushal, net reactive power 0.
Yes.
Yes, correct. That statement is correct. But what you should understand is, you have both elements there, inductor and capacitor. One is absorbing, other is delivering, and those two are exactly matched.
Yes, sir.
So that it need not to draw any other reactive power from source.
Okay.
Understood?
Sir. Sir, means I have sir tell us that in the transformer or in the machine that's it is very useful reactive power. That's why I'm asking.
Very, very simple. You think in the way of network theory. If you don't have inductor and capacitor, where is that reactive power?
No reactive power.
Okay. You keep a inductor and capacitor, then only there is a reactive power. But
Yes,
don't
sir.
say me as advantage of reactive power is used to create magnetic flux and electric flux. That's what we call that's an incorrect
Means-
statement.
Sir, because of it defects magnetic flux is created.
I don't know anything. Just we have an inductor, it is drawing current.
Okay.
It is producing magnetic flux. Then you say reactive power term and all. And you should not say in the reverse that reactive power is needed to create the magnetic flux. So the generator has to supply reactive power. What is that statement?
Yes,
Generator should supply what the load asks.
Yes, sir.
Yes or no?
Yes, sir.
Okay, to create magnetic flux, are you supplying reactive power? No, it is demanding.
Okay.
It's demanding. It's demanding some reactive current. That's why the generator has to supply it.
Okay, sir.
Okay.
And sir, transformer and machines means generator and other machines, they are absorb and deliver reactive power.
Definitely. Definitely. Yes.
Okay.
But convention is what?
Yeah, inductor is absorbed. And
That's why they will say it is absorbed and they will give it.
Okay.
Okay, but strictly
Means
speaking,
always we consider like that. Inductor will absorb.
see, one thing, Kushal,
Yes,
why I have to assume inductor is absorbing, capacitor is delivering?
Sir, it
Why?
is convention create.
Convention. Not only that, Kushal, our power system engineers, olden engineers, has designed the power system analysis in the power domain,
Yes, sir.
not in the energy domain. If they have analyzed this in the energy domain, I don't have an issue of reactive power at all.
Okay.
Because while I am summing up, that will be cancelled out, right?
Yes, sir.
Net energy I will take all the time.
Yes, sir. Means for a one cycle it will cancel.
Yes. For one cycle, reactive energy will be cancelled out. Resultant is a net energy, right?
Yes, sir.
So if you do in the energy domain, there is no concept of reactive power at all. But as we are doing in the power domain analysis, we are taking up these terms in a separate manner, active and reactive.
Okay, sir.
Okay.
Means the reactive power is not a loss
It's not a
in
loss.
terms of. Okay.
Then you can ask me, sir, it's not a loss, then why we are bothering about it?
No, sir, it is flowing in the line.
Okay, flowing in the line then.
It is not a loss. It is not a loss, but flowing in the line, sir, means.
Flowing in the line, then
We
what's the
have-
disadvantage?
No, sir, we have inductor and capacitor. We cannot neglect that. That's why.
No, it's flowing in the line. Your statement is perfect. Then what? It's flowing in the line, then what? On the behalf of that, there is some excess current flow.
Okay.
There is an excess current flow in the line.
Sir.
Then there is a more voltage drop in the line,
Okay.
causing for fall in the receiving end voltage. That's the problem of reactive.
Okay. Sir.
Understood? Energy wise, I don't have an issue.
Okay, sir.
But voltage drop wise, I have an issue with the reactive power.
Yes, sir. Understood.
Again, you can say one more relation. As you have more current flow, energy loss in the line is more. Energy loss in the line is more
Yes, sir.
because of resistance effect and all, not because of inductor and capacitor.
Okay, sir.
Okay.
Okay, sir. Understood.
Yeah. So any other doubt you have, Sean?
No, sir.
Anyhow, these terms will come again and again as we proceed further in TND. Okay. Any other doubts you have? Please raise your hands. Please raise your hands if anybody having doubts. Yeah, so I think nobody's having a doubt. Thank you.